C'est pas... Yeah. I think... So, I resume... yesterday I introduced the notion of topos E associated to some site Cj. So I gave general definitions, and of course, when we think about general definitions, we need to have examples in mind. So, of course, examples should be made out of things we already know in order for this notion not to look too hard to adopt. So, the first example, of course, is the topos of sheaves on a topological space. So, at least the notion of topological space is familiar to everybody. Of course, the full category of sheaves on a topological space is something which maybe is not familiar to everybody. It looks huge, and in fact, it is huge. In particular, I stress the point that objects of a topos never make up a set. It is much bigger. Just as a category of sets. You know, there is not a set of all sets. So exactly in the same way, there is not a set of objects of any topos. Another example, another family of examples of toposes is, of course, the very important family of toposes associated to a category without topology. So these are the toposes of pre-sheaves on a category, and so I gave the example of the topos of simplicial sets, but maybe before thinking about this example, which is already quite subtle, we may think about another case, which is the case of a discrete group. If you consider a discrete group, a discrete set theoretic group, you can consider it as a category. The category consisting in one object with automorphism, and the automorphism group of this object is G. Okay, so you consider this as a category. Then you have the notion of you have the associated pre-sheaf topos, which is usually denoted BG. So this is a so-called classifying topos of the group G. So what it is, it consists in sets endowed with an action of the group G. So this is something which is very familiar to us. We can call that the topos of actions of a group. For instance, you may think about the category of k-linear objects in this topos. So what it is a category of k-linear representations of this group. So this is something extremely familiar. Okay? And of course, it is here I am talking about linear objects. Of course, in the same way, when you are considering the topos of sheaves on a topological space, there is the associated category of k-linear sheaves, for instance, on this topos, on this topological space, and this also is very familiar. You see, so in fact, these two examples are the two basic examples we have to keep in mind. And in some sense, the notion of topos is the only natural notion which puts together topological spaces and groups. more precisely, sheaves on topological spaces on the one hand, and actions of groups on the other hand. Another important remark here is that, of course, groups are extremely important in mathematics. They are everywhere in mathematics. But if you think about it, you realize that, in fact, the reason why we are interested in groups is not exactly groups themselves. We are interested in actions of groups. We are interested in groups acting on something. So this means that, in fact, when usually when we study a group, we are interested not exactly in this group, but in the associated topos of actions of these groups. Okay, so this is a remark. Here, we can, as we are considering examples, we can immediately slightly generalize this example in the following way. By now, we consider the case of a group which is no more discrete, but pro-discrete. So this is a topological groups with a base consisting in open subgroups. Okay, in that case, you have an associated category defined in the same way. This is a category of discrete sets endowed with the continuous action of this group. And in fact, proposition you can try to prove is the fact that this category is also a topos. So in order to prove it, you have to understand what is the natural site for defining this topos. Here, when the group is discrete, it is quite easy. When the group is pro-discrete, of course, so when the group is discrete, it is trivial, as the group can be considered as a category without topology. Here, when the group is no more discrete, it is pro-discrete, then we have to think a little more with the definition of a good site for defining this topos. But the important point is that this also is a topos. And this type of toposes can be called with a natural name. We can call them Galois toposes. And in fact, this family of toposes are extremely important in the theory of toposes, and we will come again, we will say much more about them. Yeah, here maybe I can make a few extra remarks. So yesterday we introduced the notion of point of a topos, and I told you that, for instance, even in the case of the simplicial topos, the category of its points is something very subtle and interesting. So here, for this type of toposes, we can wonder what are the points. So when the group is discrete, you can easily prove that this topos has only one point up to isomorphism, and the automorphism group of this point is G. Okay? But when your group is pro-discrete, it is no more true. And in fact, this topos may have many points, and the automorphism groups of these points are not necessarily equal to G. So here, in fact, we have a very striking phenomenon, which is the following. Suppose you have two groups, G1 and G2, you consider the associated toposes of actions of this group, and you wonder whether it is possible for these toposes to be equivalent. Of course, you understand that if G1 and G2 are isomorphic, the associated toposes are equivalent. But you wonder, is the converse true? And if G1 and G2 are discrete, the converse statement is true. If you have two discrete groups whose associated toposes of actions are the same, then these groups are isomorphic. But when you are considering pro-discrete groups, it is no more true. it may happen that you have completely different pro-discrete groups whose associated toposes of actions are different. In fact, we will see examples later because you see, I am sorry, presently I have to say that most examples will be studied later because what happens in the theory of toposes is that even to study the first basic examples, you already need to have developed the general theory. This means there are no easy toposes. So it can happen that, for instance, G1 and G2, two topological groups, do not even have the same cardinal, the same cardinality, but their associated toposes are the same. So by now, if you think again about the fact that what you are interested in is not exactly groups, but actions of groups, you realize that in some sense, the notion of classifying topos of a group is a better notion than the notion of group itself. Because this is really what you are interested in, and the two notions are not equivalent. I remember that many years ago, I was stricken by a funny reflection of a colleague, Christophe Soulet, who told me that if you read the original famous text of Galois, which in fact introduced the notion of group, so he told me that in fact, the notion of group does not exactly come from the text of Galois. It comes from the interpretation of Galois 20 years after his death by the first mathematician who began to read him. And he told me that if you read carefully at what he writes, he's not talking about groups, he's talking about actions of groups. Okay, so this I wanted to say, so these examples to have in mind. And in fact, I really think that the only examples of toposes which are more or less clear for us, clear in our mind, are these types of toposes, classifying toposes of groups. Because even toposes of sheaves on a topological space, there are things which for us are extremely difficult to just to figure out in our mind. But we can work with them. Okay, so I already told several times that toposes are huge objects, and as they are huge objects, you may wonder maybe they are too huge to work with. You cannot work with them because anyway there are all these objects are not even a set. How can you work with that? So you can wonder how to work with toposes. Are toposes useful? And the answer is the most important answer we can give is the following. What you can do is to consider invariance of toposes. So what does it mean? It may mean objects which you associate to toposes. It may also mean properties of toposes, or it may mean constructions which allow you to construct a topos from another topos, which are invariant. What do I mean by invariant? I mean invariant by equivalencies of toposes. So there are many of them, in fact, and you know many of them. So for instance, all cohomological invariants in mathematics are invariants of toposes. They can be defined at the level of toposes, and of course, this, you know that we can compute with this invariance. So another very important thing is the notion of homotopy invariance of a topological space. Of course, the fundamental group pi 1, and the higher homotopy groups pi n, for n at least 2. And in fact, it has been proven already in the late 60s or early 70s by Artin and Maser that homotopy invariants of topological space are invariants of toposes. They can be defined at the level of toposes, and when you specialize these topos theoretic invariants to the topos associated to a topological space, then you recover your usual invariants. So homotopy invariants, homotopy groups are also invariants of toposes. In the lecture yesterday, we also considered another invariant, which is a category of points of a topos. You see, this is an invariant. Yesterday, we also introduced the notion of subtopos of a topos. So I remind you that if we have topos E, what is a subtopos? It is another topos, E prime, together with morphism J. So I remind you that a morphism of toposes consists in two functors, and you call that a subtopos when the direct image part of the morphism is fully faithful. So this is a definition. Okay, this is a definition, let's say, of an embedding of toposes. And by now, you can call the subtopos an equivalence class of such embeddings. When you have two such embeddings, you say they are equivalent. When there is an equivalence of categories, which makes the diagram commute up to equivalence. Okay, so this is the notion of subtopos, and then you can verify that the subtoposes of a given topos constitute a set, in fact an ordered set, a set together with a partial order. And so, if you consider a topos, you can consider the associated set of subtoposes together with the natural order on this set. This is yet another invariant of toposes. And in fact, there are in fact, there are infinitely many invariants of toposes. So the topological, cohomological invariants, which have been much used since the 20th century in mathematics, are only a particular case of invariants of toposes. So the first basic idea we have to keep in mind when we want to study toposes, to make use of toposes, is to consider invariants. And then we need an open mind, not to consider all the time the same invariants, but to be free to consider other invariants. So by now, the second point of view, which is extremely important, is the following: what can we do with invariants? We said that toposes are too big in some sense. They are huge objects. So you can say, okay, if we consider invariants, this is yet another construction, more or less technically demanding construction from toposes. So it should be even more complicated, and it should be even more difficult to work with them. So how is it possible that you can work with invariants of toposes? So here, what you can do is the following. When you have an invariant of toposes, your topos is, the toposes you consider are associated with some sites, and then what you can do is to express your invariant in terms of the defining set of your topos. A topos is something, in some sense, you never see, because it is too big. You don't have any hold on it. What you have in your hands is a defining site, which is something manageable, much more, much smaller. Site consists in sets. You can work with them. And so what you can do is to try to compute or to relate your invariance in terms of the defining sites. And so yesterday, for instance, I gave you an example of that. At some point, we were interested in the invariant consisting in points of a topos, and we expressed that in terms of a defining site. We said that it is expressed as so-called flat J-continuous functors on the underlying category C. So this is a typical example of relating an invariant with a defining site. We can also talk, for instance, about cohomology. So cohomology is associated to a topos, but you can express it in terms of a defining site. So this is called Church cohomology. You can also, when you consider cohomological invariants, you may associate to that derived invariants. So, for instance, for people here who know algebraic geometry, a very important derived invariant consists in the trace of the Frobenius endomorphism acting on cohomology. And when you are interested into this thing, of course, you know that the most important result, the most central result of algebraic geometry in relation with this object, the trace of Frobenius acting on the action of Frobenius on cohomology, is the so-called Grothendieck-Lefschetz fixed point theorem, which tells you that the alternate trace acting on cohomology is equal to the number of fixed points of your underlying scheme acted on by the Frobenius endomorphism. And this also, you see, is an expression of an invariant, a very elaborate invariant of the topos, in terms of the underlying site. In fact, here, even in terms of the underlying category. So this is yet another example. By now, in order to finish this part one, I want to give a last characterization, which is the characterization of the ordered set of subtoposes. So suppose you have such a topos E. Okay. And your topos is defined by a site, which is an underlying category endowed with a Grothendieck topology. And then here you are interested in subtoposes E prime of E. And you may wonder, is it possible to express the set of subtoposes of your given topos in terms of the underlying site? And here there is a theorem, a very beautiful theorem, which tells you that to consider a subtopos of a given topos is equivalent to consider a Grothendieck topology on C which contains J. So you just allow more covering. You keep the same underlying category, and you just allow more coverings of the objects of C. So to consider a subtopos of your given topos is exactly equivalent to consider a Grothendieck topology on C, which contains the topology J, which defines E. In fact, this equivalence immediately has consequences because if you consider Grothendieck topologies, you immediately see that it is possible to define the intersection of a finite family of topologies. It is also possible to consider the union of a finite family of topologies, which is the topology generated by the topologies in your family. So this means that if you consider here subtoposes, there is a notion of intersection, there is a notion of union, If you refine that, you can even realize there is a notion of complement of a topos, of a subtopos. Exactly as in topology, if you have an open subset of a topological space, then you can consider its complement. The complement of an open subspace is a closed subspace, but here it works also at the level of subtoposes. Okay, so we have this very nice characterization theorem, and so this is really a basic principle to study toposes, consider invariants, and compute them, express them in terms of defining sites. Here I need to add an extra remark before moving to part 2. The extra remark is the following. It is the fact that we already said that topos is defined by a site. When you have a site, you have an associated topos. But by now you may wonder about the converse. When you are given a topos, is it defined by a canonical site? The answer is no. It means that for any given topos, it is defined not by a site, but in fact by infinitely many sites. So this means that in practice, when you are considering toposes on sites, at least that you have a topos defined by a site, in fact, you can immediately construct many other sites which define exactly the same topos up to equivalence. And later, in part 3, we shall see that toposes can be defined not only by sites, but also by theories. So this is yet another family of presentations of toposes. And here, very basic, very important principle, which is at the basis of the last part, 4th of my lectures. So this is the principle for the work of Caramello I will introduce, is the fact that this is an extremely interesting and fecund point of view of mathematics. So this means as soon as you have a topos, which is defined in several different ways, you can consider invariants of the topos and compute them in the different presentations. So you consider one invariant and you make different computations in the different presentations of the site, of the topos. And then it may happen, or in fact in practice it happens very often, that for a same topos you have presentations which not only are different, but which belong, for instance, to different parts of mathematics. So this means that a single invariant is expressed in presentations which belong to different parts of mathematics. And so it means that this invariant will be expressed in completely different terms. And so you get completely different expressions for the same invariant. And so this means that the different expressions you get are equivalent one to the other. And this is an extremely general principle to, in fact, relate different phenomena in mathematics. So I will, later, of course, I will give examples of that. Okay. By now, I want to come to part 2, which will be shorter. So part 2 is toposes as general universes, general mathematical universes. So here the basic idea I want you to retain is the fact that in some sense all toposes are just as good as sets. They have almost all basic properties of sets. So I immediately state a proposition. So the proposition is the following. You consider an arbitrary topos, and I immediately give a list of properties of this topos. First, the first property is that E has arbitrary, when I say arbitrary, I mean small limits. Small, I mean indexed by categories, by small categories. Categories where the collection of objects is a set. So arbitrary limits, not only filtered limits, but arbitrary limits, in particular finite limits, and then and also filtered limits. The second property is the same with co-limits. The third property is that it has images. So if you have a morphism, in your topos, then there is a notion of image of this morphism. So what is the image? You consider the subobject of B through which the morphism factorizes. And then the statement is that this collection of subobjects has an element which is smaller than all other elements. So it is called the image. Okay, so you can factorize this in this way. So here, this is a monomorphism, and this is an epimorphism. And this is called the image of F. It has images, and the second condition is that the formation of images is compatible with base change. Okay, there is a notion of base change because in the topos you have arbitrary limits, projective limits. So there is a notion of base change, and the formation of images commutes with base change. The fourth property is the following. So I already said repeatedly that a topos is never small. The collection of its object is not a set. But E has a small generating family of objects. So this means that in your topos you can choose a set of objects such that any object in your topos is isomorphic to a quotient of a sum of elements in your family. This is exactly the statement I just said. Any object in the topos is isomorphic to a quotient of a sum, a disjoint union, of objects in your generating family. Okay, so you have these properties. The last properties I want to say right now is that E has exponentials. So what does it mean? It means that if you have two objects, A and B, you can associate to them another object which is B to the power A, which has the same meaning as in the set theoretic context. So what does it mean? It means that this it means the following. So your two objects A and B are given, and you consider the following functor to any object in your topos. You associate the set of morphism from E cross A to B. So you see it is a contravariant functor, and the theorem is that it is representable by an object. So this is the homomorphism from E to B to the power A. So the theorem is that these functors, the functors of this form, are always representable by objects in your topos. So this can be understood as spaces of functions from A to B. So you see that when you have these properties, you understand that everything or almost everything you are used to do in the set theoretic context, you can also do in an arbitrary topos. For instance, these properties are more than enough to do everything you are used to do in algebra. And this, when you add that, it is sufficient to develop analysis because you have spaces of functions. So this means that toposes are mathematical universes which are as good or just as good as sets. In fact, here I don't say exactly as good, I say almost as good because there is something, a property which many people allow for sets to have, and which is not verified by toposes in general. It is the axiom of choice. So when you are working in set theory, you can decide whether to accept or not the axiom of choice. But when you are working with toposes, the axiom of choice cannot be verified. What would be the axiom of choice? So the axiom of choice in that case, what would it be? It would be that any epimorphism from an object A to an object B has a section.
External projection.
Yes, exactly. And this, of course, so when you are working with sets, you can add that as an axiom. When you are working with toposes, in general, it is just, if you add that, it becomes contradictory. So if it was true, for instance, there would be no cohomology in mathematics. So the axiom of choice is not verified in general in a topos. In fact, logicians have studied the very particular types of toposes for which you can accept this axiom, but they are extremely particular and not very interesting. So in fact, when you remark that, you may wonder whether, after all, maybe we could decide not to accept the axiom of choice even in the case of sets. But people do as they want. Okay. Okay, so here I have given to you a family of properties of toposes. But I immediately have to say that, in fact, there is a converse to this proposition. And the converse is that if you have a category E, which verifies these properties, not only 5 will be a consequence, but you consider a category which has these 4 properties, then it is a topos.
Don't you need a subject classifier?
Excuse me?
Don't you need a subject classifier also?
No. The subobject classifier, I'm going to talk about it immediately, but we don't need it. In fact, we don't even need the full strength of these properties. We could even replace these properties by less strong properties, but it doesn't matter for us. It would be enough for a category to have properties not as strong as that, to be a topos, and so to have these properties. So this is the so-called Giraud theorem. So this was proved by Grothendieck, of course, and Giraud in the other direction.
Doesn't the category of abelian group satisfy these properties?
No.
Probably something to do with observation. The rest are satisfied.
No, but for instance, you cannot take the quotient of abelian groups. Okay.
I mean, this family of properties looks self-dual, right? No, generating but not generating.
Generating family.
Okay, fine. Yes.
Okay, but so this is enough to characterize toposes. So this means that when you have a category verifying these properties, it is equivalent to the category of sheaves on a site. Okay, and in fact, this characterization is quite useful because it allows you to immediately say that many natural categories are toposes. So for instance, here I told you that if G is a pro-discrete group, then the category of actions of G on discrete sets is a topos. So when you want to construct a generating site, it is not so obvious. But it is much more direct to verify that these properties are true. They are verified by this category. So it is enough to say it is a topos. And in fact, you can apply this criterion to much more general categories. For instance, suppose you have a topos E. Okay? And by now, as in E, you can talk about products, and it has a meaning to talk about a group object in E. It is just an object in E endowed with a product morphism, okay, with also a unit element. So the unit element is a morphism from the finite object to G. Okay, so one denotes the finite object, and you also have an inverse, a morphism of, which allow you to inverse. Okay, so it has a meaning to talk about a group object in a topos. And then, when you have a group object in a topos, there is an associated category. So this is a category of objects in the topos endowed with an action of G. So what is an action? It is a morphism from G cross E to E, verifying some properties. Okay, so here I define a category, and using this criterion, you verify very easily this category is a topos. It is called the classifying topos of G. And this is very useful because, for instance, you can consider an algebraic group or a real analytic group or a complex analytic group, a Lie group, any type of group in any type of mathematical structure you can think about. And always, these groups give rise to a topos using this construction. Okay, so this means that, of course, in all cases, you can construct explicitly defining sites. And in fact, it is interesting to do it. But it requires some work. Whereas, when you apply this criterion, you immediately see this category, for instance, is a topos. So it is quite useful. Here the idea is the following. It is the idea that the notion of topos is very stable. You see, so yesterday I explained that the process which goes from a site to the associated topos can be understood as a completion process. You replace the category C endowed with this topology by a much bigger category, which verifies these very nice properties. It is stable under all natural operations you can think about, because they are the natural operations you are used in the context of sets. Okay, so this is a completion operation. So here, the converse part of this theorem tells you that in the opposite direction, a category which is complete enough to satisfy these properties is a topos. Okay, so this means that as soon as a category is nice enough, complete enough under natural operations, it is a topos. And so this means the notion of topos is very stable. When you start with a topos and you make a natural construction with a topos, usually what you get is a topos. Yes?
This is base change in the third property. This is the pullback or...
Yeah, pullback. This is, so this means this means the following. So here you have a morphism. Okay, so we are considering a morphism F from from A to B. Okay, you suppose this is over a base object. Let's call it I don't know, C. And here you have you make base change. So this means that you construct, here you have B prime, here you have A prime, just by pullback. And so what I am saying is that the image of this morphism is the pullback by C prime to C of the image of this morphism.
Okay, this property is satisfied by billion groups. And,
this property is verified, yeah, okay.
I mean, all the properties are satisfied by billion groups.
Okay, so this is a question. R is a category of Abel. Yeah.
Which one?
Other version of the
shouldn't you also require that the limits are also commute with base change?
Do they commute with base change? I'm not sure. No, I don't think it is true in general. No, it doesn't commute with base change in general. No, but even in the case of sets, I would say. We will discuss that after. But even in the case of sets, I don't think it is true. Okay, so this is the basic properties of toposes which we have in mind. So all of this, I said, was already done by Grothendieck and in the other direction with the help of Giro. And in fact, Grothendieck insists a lot on the fact that toposes are, in some sense, avatars of the category of sets. They are just as good, but much more general. And when you think about it, you may wonder why we are always doing mathematics with sets. Because it would be possible for most constructions in mathematics, for most theories developed in mathematics, it would be possible to make these constructions, to develop this theory, not in the context of sets, but in the context of an arbitrary topos. Okay? And here, you may at least ask yourselves this question when you are thinking about physics, for instance. So here I am not saying that by now there is a nice theory in physics developed in terms of toposes, but at least you may wonder whether it is really a natural thing that everything in physics is developed with the language of sets. So you cannot exclude the possibility that some theories in physics should be better phrased in terms of different toposes. I don't see any reason why all theories in physics should be better stated in terms of sets.
I still have an experiment to clarify that.
No, I don't have, this is just, no, for instance, some physicists, in fact, have, some theoretical physicists, try to do something in the context of quantum mechanics. So they wondered whether maybe quantum mechanics, or at least part of quantum mechanics, could be better phrased in terms of toposes, of some topos. But of course, the question is which topos? Would there be a more natural topos for phrasing quantum mechanics? So their hope would be that quantum mechanics maybe could be phrased in classical terms in the context of some well-chosen topos. But it is a question, it is not done. Some people have tried to do that, but so far what they have done is not advanced enough. But at least you may wonder that. So you see, for instance, in the history of physics, there was a model of Euclidean geometry, and at some point mathematicians introduced Riemannian geometry, and later it appeared that gravity was better phrased in terms of Riemannian geometry, or a variant of Riemannian geometry, Lorentzian geometry, than in the language of Euclidean geometry. And as a matter of principle, we can wonder the same question with toposes. At least I don't see any mathematical reason for believing that everything in physics should be phrased in the terms of sets and not developed in the context of other toposes. So it is, at least a priori, it is possible that some theories could be phrased classically in terms of some topos, and when you rephrase them in terms of the basic theory of sets, the phrasing is no more classical. So this is possible. This is a possibility. I'm not saying it is done. Yeah.
Do we have any instruments to work with real numbers in terms of arbitrary topos?
Yeah. No, we don't have the axiom of choice, but there is an equivalent of real numbers. So you see, I should have said that when you have a topos E, there is always a structure morphism, a unique morphism to the topos of sets, to the one-point topos. Exactly as any topological space has a structure morphism to the topological space consisting in one point. But this is true at the level of toposes. When you consider an arbitrary topos, there is always a unique morphism of toposes from this topos to the topos of sets. So this means that in the two categories of toposes, the basic topos of sets is a finite object. Okay, so this structure morphism, you call it F. So here you certainly have the object R, and it has a meaning to consider the pullback.
But those will be real with a kind of discretized structure.
No, but this is real. I mean, you can really. There is also F star of Q. And F star of R can be constructed inside this topos as some completion of F star of Q. Exactly in the same way.
Okay, maybe I have one.
In order to construct R from Q, you don't need the axiom of choice. You just consider Cauchy sequences, so it has a meaning.
Well, actually,
Listen to me, but non-standard analysis is a part of this framework.
This I don't know. I think it is better than non-standard analysis because the problem when you are this I don't know very well, but I think that the problem of non-standard analysis is that it is not constructive. You don't you don't have
Get it as an ultra product.
Excuse me?
You can get it as an ultra product.
Yeah, okay, but you see, this is huge thing. So whereas when you work in a topos, so it is true toposes are huge, exactly as these ultra products and things like that. They are huge, but when you are considering natural things on these toposes, which means invariants, usually you can express them in terms of defining sites, and this is constructible. In fact, a very important information about toposes is that you can compute with toposes. We are used to do that when, for instance, we are talking about cohomology, but this is not only true for cohomology. It is true for many things. For instance, all these invariants we have already talked about, the category of points, the ordered set of subtoposes of a topos, all of this you can compute with. And the experience is that when you consider invariants of toposes, you can always compute with them. So usually it is technically quite demanding, but you can do it. And when I say compute, I can even say that here the computations with toposes can even be implemented on computers. Toposes can be used for computing in a mechanical way. And so maybe I will make extra remarks on that later. Okay, so the second thing I want to say in this part 2 is so a name which you have said, which is the so-called classifier of subobject, because it is an important property. So this object, the classifier of subobject, was not introduced by Grothendieck. It was introduced by Laurent in the 70s. So this is a discovery by logicians. So what it is, you consider an arbitrary topos E, and you consider the following functor. So to any object of E, you associate the set of subobjects of E. Okay, so what is a subobject? So of course, what does it mean? It means you are considering monomorphism from E prime to E, considered up to equivalence. So then there is a property that subobjects of an object make up a set. Okay? And so this means that here you go from E to sets, and in fact in this way, using the pullback, using the existence of limits, here finite limits in toposes, here what you get is a contravariant functor from your topos to the category of sets. And so the theorem here by Laurent the theorem is that this functor is always representable. It is representable by an object which we call omega E or omega, and this is called the classifier of subobject. So what does it mean? It means that this, to consider a subobject of E is equivalent to consider a morphism from E to omega. So this is a discovery by Laurent that in an arbitrary topos, this object always exists. And of course, as it is defined as representing a functor, it is uniquely defined up to unique isomorphism. So it is an invariant of the topos, this object. Okay, so you may wonder, do we know this object in the case of sets? So what is a subobject classifier in the case of set? Yes, exactly. So then omega is a set consisting in 2 elements. Okay, to consider a subset of a set is the same thing as to consider a map from this set to 0, 1. And your subset is just the inverse image of 0. But the theorem is that this is true in an arbitrary topos. Let's make another remark in the case of sets. Of course, when you consider the topos of sets, you have a finite object in your topos, which is so the final object is the set with 1 element. Okay, so any set has a unique map to this set. And of course, in an arbitrary topos, there is always a finite object, because I said here that there are arbitrary limits. So in particular, you can form the limit over the empty category, and then what you get is a finite object. So there is a finite object in an arbitrary topos. And here we just said that the subobject classifier in the case of set consists in 2 elements. So what does it mean? It means that this object has 2 sections over the finite object. Okay? By now, if you are in an arbitrary topos, you have omega, and you have the finite object, which is usually denoted in this way. And you may wonder about the sections. But here, what happens is that for general toposes, you can have much more than 2 sections. You can have infinitely many sections, for instance. And this, in the inner theory of toposes, has a name. So the sections of the subobject classifier are called the truth values. What does it mean? In the context of sets, you have only 2 sections, which means only truth values, which are true and false. But in the context of an arbitrary topos, you may have many more truth values. If you want intermediate things between true and false. So here I am just hinting at the fact that when you are considering a topos, there is a logic associated to it. And this logic may be much more refined than the logic which is associated to set theory. So when you are considering a set, on the subset, you have a notion of complement of this subset. And the union of the subset and its complement is the whole thing. So what does it mean? It means that you have the excluded middle law. Is it? Excluded middle law. So this means that either something is true, either it is false. But you always decide. But in an arbitrary topos, it is no more true in general. So here I can just make, I want just to make an extra remark, which is in order to make a little more precise what I just said. So you see, when we are considering an object of E and 2 subobjects, E1 and E2, it has a meaning to consider the union of these 2 subobjects. It is just the image of the natural map from the disjoint union of these 2 things to E. So you can consider the union of 2 subobjects, which you denote by this sign. You can also consider the intersection. There is also a negation operation for, if we consider E prime embedded in E, there is a notion of negation of E prime. So what it is the biggest subobject such that E second intersected with E prime is equal to the empty subobject, the initial subobject. Tuple back. Yeah. And the union is the image of the natural map from E1 union sum E2 to E. Okay? And so here I am saying that if we have a subobject E prime of E, we can define its negation, which is the biggest subobject, E second, whose intersection with E prime is the initial subobject. And another information is that all these operations are compatible with pullback. So because of this, it means that these operations are defined at the level of omega. Omega has a union operation from omega cross omega to omega. It also has an intersection operation, and it also has a negation operation from omega to omega. Okay, I don't even say all, there are other operations, but I don't tell about them. But here I want to make a remark. It is the fact that we may wonder about the law of excluded middle. So what is this law? It is the fact that the negation of E prime, union E prime, should be equal to E. And here, of course, this is verified in the case of sets. It is not verified in general in a topos. So this means that in toposes, the law of excluded middle can be true or not true. When it is true, the topos is called Boolean. It is equivalent to the fact that the negation of a negation is identity.
It's equivalent to the fact that there are only two elements.
No. I think, yeah, it is. This is stronger. I think.
Oh, it means that omega is equivalent out.
Yes. Yeah. So here, so this is a topos when this where this relation is verified is called the Boolean topos. There is a lesser form of that, which is the so-called De Morgan law. It is the fact that the triple composite is equal to the negation. De Morgan.
This is always the case.
No, this is not this is not always the case. Of course, this implies that, but this is not as strong, and this is not always the case. So De Morgan, no, it is not always the case. No. So toposes which verify these properties, the so-called De Morgan law, are particular types of toposes. So here, what I want to say is that, in some sense, there is a logic inherent defined by any topos. But in lecture 3, we shall see. So here, you see, what I am talking about is the fact that when you have a topos, there is, in some sense, an inner logic of the topos. But in lecture 3, in the part 3, in chapter 3, we shall see that it is also possible, and in fact it is more important to know that in the other direction, when we have a theory, a first order theory defined with the language of logic, it is possible to associate to it a topos. So it is, I say it right now because it is important not to confuse these two things. In fact, there are not one, but two relations, at least two relations of toposes with logic. The first relation is the fact that when you have a topos, there is an associated inner logic. And the other relation is that when you have a theory, a first-order theory, in the language of first-order logic, then there is an associated topos. And this will be the subject of chapter 3. Okay, so maybe, in fact, as I have said that, I can begin chapter 3. Okay, so this is the end of chapter 2. Okay, so before I begin to define things in a precise way, I want to say in a few words what we are going to do. So here in chapter 3, we are going to consider theories. So by now I am speaking in loose terms, and after that I will make things more precise. So what is a theory? A theory consists in two things. First, a language. So here I immediately introduce the term signature, because logicians use this term, but a signature just means a language. And the second data consists in axioms of the theory. So you really can think about that by analogy with natural languages, such as Russian or French or English and so on. So what do you have? You have a language consisting in words, and you have axioms. So the equivalent of axioms in the context of natural languages is a grammar. Okay? So theories consist in that, and then when we are thinking about natural languages, of course, why do natural languages exist? They exist to express things. Okay, words are not only formal things which have to respect formal rules. They are used to say something. So, in the context of logic, what does it mean? It means that when you have a theory, you associate to this theory so-called models of T. So what does it mean? For instance, consider the theory of groups. So in the theory of groups, what is the language? So in the language, you have the first word is G, which will denote the group object. Okay? The second word is let's say M for multiplication morphism. So by now it is not a map, it is the name of a map. Just the name multiplication. Okay? Another thing which we'll need is the word inverse. And the last thing we will need is the word unit. So you see, at the present moment, we have 4 words. The word group, on the words multiplication, inverse, unit. 4 words for the language of groups. Excuse me?
What about one? What about this strange thing?
No, this, okay, so by now it is just, let's, at this level, it is not, don't even write it. No. I don't even write it. It is not part of the language of the theory. Okay, by now I'm just saying that I have a word for group. You see, here there are 2 different types of objects. Because this will be interpreted as objects, and this will be interpreted as arrows. So this means that in the basic language of the theory of groups, there are 2 types of words. One type for objects, names of objects, and names of maps. But at the present moment, they are not expressed. They are just names. At this level, they don't mean anything. Okay? By now, there are axioms. Of course, what do we have? We have the fact that multiplication should be associative. Okay? So what does it mean? It means that we are considering composed map from GDG to G. Okay? There are 2 possible paths to get there. And the 2 possible paths should be equal.
I'm sorry, I didn't understand. It is not the correct word.
Okay, so by now I am speaking in loose terms. At least you know what is associativity. After that, I will make precise exactly, everything will become precise and well defined.
In this language, there is some formula which states associates.
Yes, exactly. So this means that when I have words, it means the following. It means that when I have words, using these words, I can form sentences. Okay? So in the context of logic, these sentences are not called sentences, they are called formulas. And the axioms consist in saying that some formulas should be true. Okay, so for instance, associativity, it will be expressed as, in fact, a relation between 2 formulas, which should be equal. The same for the inverse. The inverse is defined by some properties, the same for the unit element. So there is a finite family of axioms, and in fact, you have written them many times. Okay? By now, what is a model of T? So usually, mathematicians are used to considering models, in considering set theoretic models. So, models of T in sets, what it is a set G. So you see the first word, which is the name of an object, will here become the name of a set. Then the things here will become names of maps. Okay? There are plus 3 maps. And here the 3 maps, because I have written here G 2 times, the first map becomes a map from G cross G to G. The second map becomes a map from G to G. And the last map becomes a map from the final object to G. Okay? And what I mean by a model, I mean that the axioms defining the theory should be verified by this set endowed with these 3 structure maps. Okay? So it has a meaning in sets, but it has also a meaning in an arbitrary topos. Because in order to define this type of structure, what do we need? We need the product of 2 objects to be defined, and it is certainly defined in a topos, and we need a final object. And the topos certainly has a final object. So it is possible to talk about a group in an arbitrary topos. And in fact, for most theories in mathematics, it is possible to talk about models of these theories in an arbitrary topos. Because toposes have all the properties I have written before. Yes?
What is the difference between your notion of model of group in toposes and group object in toposes?
No, it is the same. There is no difference. It is exactly the same. Okay, here I am just introducing the word model. No, it will become clear later. But you see, here I am taking the example of group, but I could take any theory consisting in a language and axioms. You see, and here I can make a comment, which is the fact that logic is something extremely flexible. So we are used to work in mathematical theory. So for instance, in algebra, in topology, and in this context, objects are not very flexible. So for instance, if you think about algebra, there are linear structures and non-linear structures. And in some sense, they are separate one from the other. Whereas, in the context of logic, in some sense, everything belongs to logic. Logic is just a language and axioms, and you can change the axioms exactly as you want. You can add axioms, you can remove axioms, you can replace an axiom with another axiom, you can introduce new words in your language. So it is extremely flexible. Okay? In some sense, without structure at all, but extremely flexible. And so what we will see, in fact a little later, is that when we consider not all theories, but the theories in an extremely large families of theories, it is possible to associate a topos to them. And immediately it allows you to consider huge families of toposes. So I would say much more toposes than in the context of geometry. So if you are working in geometry, usually the concrete objects you consider in geometry are not so numerous. So you can draw a list. There are elliptic curves, abelian varieties, there are reductive groups, but there is an explicit family of reductive groups and so on. If you think concretely about what you are really studying, in fact, the families are not so big. Whereas in logic, it is, you can, if I ask you to define theories, you will immediately begin to write one theory, a second theory, a third theory. You don't even have to think about it. You just choose axioms in a, no, it is extremely flexible. So it doesn't mean, of course, that all theories are as interesting one to the other. Some theories are much more interesting. But at least at the level of definitions, you can do everything you want. Okay, so when you have such a theory, where you can consider models of this theory in sets, and more generally in a topos. And so this means that when you have a topos, you can associate to it the T models with coefficients in E. And these are objects of the topos, but usually this will become a category. So there is, for instance, if I consider the theory of groups, of course, if you consider all, for instance, set theoretic groups, they form a category. What are the morphisms? They are the maps between groups which are compatible with the structure maps. And the same for all theories. Yes?
When you say objects, in first order?
At this level, at the present moment, not even first order. Because it is possible to consider models even of higher order theories, because I explained earlier that in toposes you have exponentials. So this means you have spaces of functions. So it is also possible to define higher order models in toposes of higher order objects. But of course we will immediately come to first order. I will say why. Because by now, so to any topos, I can associate the category of models of your theory in this topos. But of course, as we are mathematicians, we are not only interested in objects, we are interested in relations between objects. So what is the relation between two toposes? It is a morphism of toposes. So a morphism, I remind you, is just a couple of adjoint functors, such that the pullback functors is compatible with finite limits. Okay, and by now, some property which I may ask for is the following. When I have such a map, I would want to relate in a natural way the model of the theory T in E1 and the model of the theory T in E2. Okay? So here you remark that the direct image functor is only compatible with limits, with projective limits. Whereas the pullback functor is compatible with arbitrary colimits and finite colimits. It is a much better functor. It is an exact functor. And because it is exact, it will be much better if we want to transport structures. So because of these properties, we are interested in theories such that there is an induced functor between which goes in the other direction, induced by the pullback functor, from the models of T in E2 to the models of T in E1. But of course, this property will not be verified by all types of theories. And here at this point, we have to drop higher order logic. Why? This is because the formation, because this functor is not compatible with exponentials. So for this reason, we have to forget higher order. So this means that by now T is first order. Okay. But by now, we may wonder which type of first-order theories automatically induce this type of functors. And there is a precise answer to that, which I am going to give later. These are so-called geometric theories. Okay? But I immediately tell you that, for instance, algebraic theories are geometric. All algebraic theories are geometric. And in fact, also, for instance, if you think about theories which are expressed in terms of order relations and things like that, they are also geometric. In fact, I would say, all parts of mathematics, when you are considering some type of objects, it is possible to formalize at least some parts of the properties you are interested in terms of geometric theories. So this means that there are geometric theories everywhere in mathematics. And geometric theories are just the theories for which you have such an induced functors, not only for which you can not only talk about models of your theory with coefficients in a topos, but also about induced functors. And by now I can state, so far I didn't give definitions. I first wanted to give you an idea of the general setup. Precise definitions will be given tomorrow. So I consider an arbitrary geometric theory. So, for example, any algebraic theory. So all theories in algebra are geometric, and I repeat, in fact, there are many more theories than geometric theories. And then for such a theory, you have this functor from toposes here, where is it defined? It is defined on the true category of toposes, and it goes to the true category of categories. And so the key theorem here, which has been proved, I think, in the mid-50s, is the following. It is the fact that this functor, which is a contravariant functor, you see it reverses the direction of the arrows. This functor is always representable. This is representable by some topos, which is uniquely defined up to equivalence, and it can be denoted into this way, and it is closed the classifying topos of the theory. So the property which defines this functor is the following: it is the fact that for any topos E, the T models with coefficients in E, so this is a category, is equivalent to the morphism from the topos E to the classifying topos. So in particular, the set theoretic models of your theory, so this is a category, is equivalent to the category of morphism from sets to your classifying topos, and this, by definition, is the category of points of the classifying topos. So, for instance, there is a topos whose points are the category of groups. There is a topos whose points are the category of rings, or commutative rings, or local rings, or the category of models over a ring, and so on. You see that, okay, so another information I give you is that in the other direction, so this is an extra remark, but extremely important, it is the fact that any topos can be obtained in this way.
There is some kind of loop space.
Excuse me?
So this is some kind of loop space.
Yeah, it is a loop space. What do you mean? You mean the category of points?
No. Okay. Never mind.
Yeah, so any topos can be obtained in this way as the topos, as the classifying topos of some theory, or not only of one theory, but of infinitely many theories. So, so I have to finish right now. So just a last remark. So you have to, you see, today I am speaking loosely, and I want you to have in mind the following. So you see there is this operation which goes from a theory to its classifying topos. So what is this? So a theory is an object in logic. Okay, it consists in a language, words, and axioms. So this is a grammar, a syntax. Okay, and in order to understand, to know the classifying topos is the same thing as to know this the category of models of this theory in an arbitrary topos. So what does it mean? It means that to know the classifying topos is equivalent to know all possible expressions of your theory. So moving from your theory to the associated topos is a mathematical incarnation of going from syntax to semantics, from logic to mathematical content. You see, when you have a theory, what is its mathematical content? It is all objects you can consider in your theory. Okay? Not the axioms, but the objects which verify these axioms. The objects which verify the properties you have specified. So this is exactly as going from a natural language, consisting with words and a grammar, to everything it can express. Okay? To the meaning, all meaning you can do. Okay? So here there is something very striking. It is the fact that when I am pronouncing the following words, I say, when you have a theory, I consider the mathematical content of this theory. So when I use these words, I have a feeling that the expression mathematical content of a theory is no more mathematical, it is meta-mathematical. But what this theorem tells you is the fact that this meta-mathematical concept of mathematical content of a theory, in fact, can be studied in a mathematical way, because a topos is an object in mathematics. So this theorem allows you to do, in some sense, to do meta-mathematics with mathematical tools. Okay, you see here what you do is you represent the mathematical content of a theory by a topos, which is a topological object. Okay, and so before we have seen this operation of going from a site to the associated topos. Here we have the parallel operation of going to a theory to its classifying topos. And this operation embodies the fact to go from syntax to semantics. And as I told you, it may happen that different theories have the same classifying topos or have equivalent classifying topos. So what does it mean? What is this phenomenon? This phenomenon is a phenomenon of traduction. You have two different languages with two different grammars. So let's say Russian and French, for instance, and you can translate. Okay? But here you have to be careful with translation, because when we think about translation, we think about dictionary, which means for one word you have one word and so on. So this is still at the level of logic. But it may happen that you have two different theories without dictionary. You cannot translate word for word, but the mathematical content of these two theories is the same. So this is a much more subtle concept of traduction. You have here a possible traduction without dictionary. And this type of phenomena is extremely interesting in mathematics. In fact, there are many instances, and I can even say that this is the reason why I have been interested into all of this when I learned about it, thanks to Caramello a few years ago. This is because I am specialized in the so-called Langlands program. The Langlands program consists in relating two completely different theories. The theory of Galois representations and the theory of automorphic representations. And here, what this theorem allows is to build a theory of relations between the mathematical contents of theories. And this, for me, is very interesting, and I think of extreme importance in mathematics. So when I learned about it a few years ago, I was completely baffled, because this theorem has existed since the 70s, and I had never heard about it. So for instance, most algebraic geometers don't even know about it. I asked the question to many of them, they have never heard about it. So this is an example of lack of communication between different communities in mathematics. Okay, so I think I stop right now.